Okay, thank you. How much time have I got? 15, 20? Okay, that's fine. So today I want to talk to you about real-time radar signal processing. It's not much about AI, this talk. It's also to show you that sometimes signal processing algorithms can help you reduce the requirement for running estimations, for example, in the case of radar signal processing. So first of all, I want to talk to you about what is a frequency modulated continuous wave radar, very briefly, probably in 3 minutes. It's a very big topic. I will try to do my best. And then I want to talk to you about how we can do signal processing on these radar signals with low memory and low latency components, just by using adaptive resonant infer neurons. And then I would like to conclude and maybe show a demo if we have time. Otherwise, I'm around. I can also show it to you. So radar signal processing, FMCW radar, frequency modulated continuous wave radar. They serve multiple applications from IoT devices, for example, gesture recognition. There was the Google Solai, a very big project that was in the phone. I think they failed, but it might be back at some point. It's used a lot in defense, where you have to do tracking of drones or objects that are flying. Also in space, you see debris tracking with radar systems. How does a radar or frequency modulated continuous wave radar works? Well, it works by emitting radio waves, and radio waves of increasing frequency. So typically what you have, you send a signal with a transmitter that has increased frequency, like you see here in time. It's like a chirp. It's an increasing frequency signals. And you have a linear frequency modulation. So if this is frequency and this is time, the chirp will be whoop, something like this, if it would be in the audio spectrum. And then another antenna would receive this signal, and you need to mix the two, the transmitted and the received, in order to be able to extract beating frequency. And the beat frequency will tell you basically the distance of the object, because we know the speed of light, and there are some equations that relate the distance with the beat frequency. I will not go too much into the equations, but this is a very basic idea how a frequency modulated continuous wave radar works. Other than that, one could start doing fast Fourier transform to extract the distance of the object. So basically, on the beat frequency, you do a fast Fourier transform on all of the chirps that you get, and then you get the distance. You can extract velocity given the phase evolutions across multiple chirps. So basically, you have a frame that you see here. You do the range. You do another FFT on the second dimension, and then you basically are able to know the speed at which the object moves in the environment. In practice, you basically have to record frames out of this system. So record multiple chirps, store them in a frame, and do a 2D FFT. One first FFT for the range and a second FFT for velocity. You can also do beamforming and other kinds of advanced processing, but we are not going to cover those ones. But what you see here is that all of this pipeline is dense. Lots of data, lots of frequency Fourier transform. So there is a bottleneck today. As we see an increased usage of this type of radar systems, modern radar that are found also in automotive, for example, they typically have 48 receivers, 48 transmitters, antennas, and the resolutions of the ADC and the resolutions of the frequency increases. So there is an increased frequency, increased resolutions. The ADC becomes very costly, and they have dense computations, and they require large data bandwidth, high compute resources, and increased latency. So for example, for 48 transmitter receiver, state of the art is about 100 gigaflops per frame that you require to do the computations, and 10 teraflops per second. So it's become quite heavy, right? And so for the edge, the question is, how can we deal, right? How can we reduce this? Or what can we do that is different still to extract? In the end, we only want velocity and range of the target. So for this, actually, it's a line of research that we started many years ago in a team also where I was involved previously, and also I think Manolis was there, and Amir were part of this team. So we were thinking about how to rethink the radar pipeline, in which, for example, you have a transmitter antenna, a receiver antenna. You do this in-phase mixing to extrapolate the bit frequency, and then you arrive at the ADC level. Here, instead of doing full dense FFT, we would like to extract only sparse information and maybe use event-driven or spike neural network to do classification. So this is kind of the novel part or the novel aspect that I would like to discuss with you. So since then, we had quite some development. And the idea, of course, is then to use state-of-the-art neuromorphic chips that are also efficient to do this type of radar signal processing. But first of all, we wanted to look at what type of elements can we use in order to extract frequency components of a signal. And one of such elements is the so-called resonate and fire neuron. So resonate and fire neuron is a single neuron unit whose equation is described here, and we're going to look into that in a moment. But basically, the membrane potential, or you say this neuron, actually is a complex neuron, so it accepts real and complex values, and its store is potential. I call it membrane potential, but it's the internal value into a complex number. It is sensitive to input frequency because the input frequency are in its equations, and it can exhibit very complex dynamics. And the neurons have a natural frequency. For example, if your input is tuned to the same frequency of the internal resonant frequency of the neuron, then the neuron will increase its own activity, so would resonate with the input. And so with this type of element, it seems to be compatible with the type of signal that you have in RF or in frequency modulated wave. So what you could do, and this is something that we published a couple of years back, is you could have a bank of these resonate and fire frequency neurons, and you could do exactly the same operations as a frequency Fourier transfer, but in this in a way that is fully parallel. You get the chirp by chirp from the radar. This is sent as an input to a bank of resonate and fire neurons that have different resonant frequency. And then what you would see that over time, imagine that this is the internal state of 200 neurons. All of these neurons would have an amplitude that is equivalent to the frequency Fourier transform. So it is possible to do fully parallel equivalent computations as a traditional fast Fourier transform just with resonate and fire neurons. However, the drawbacks of this method is that, of course, it is equivalent. It's not a drawback. That's what we want. We want an equivalent output of the fast Fourier transform. But we can do this in parallel and process the temporal data. The trade-off is that we're still relatively expensive in the sense that you have to compute all of the neurons, right, in parallel. So one neuron for each frequency. And many of these frequency components, they're not very interesting for us because they're just very low or very noisy. So the solution for us would be to have an adaptive frequency neurons that allow the frequency of the neuron to change over time and to reach the peak of the spectrum. Because in this case, for example, if this is a radar signal, you would have 3 targets at 3 different distances: very far, close, close, and closer, right? So the peaks is what we are interested in this case. And so how does it work? So ideally, we would like to have a neuron that changes their frequency. So let's say we initialize the state of the neuron here. It's still adaptive resonant and fire neurons, but we would like the neuron to move slowly or fast to converge to the peak frequency. And so with one single unit, you could do the spectrum of an entire signal. This is possible. We need to have a neuron that update its own internal omega, its own internal frequency. This is the update rule. It's actually adapted for a continuous system. So now we are looking at a neuron that is a dynamical system and in which the omega changes with time and depends on the complex values of the input signal. So it basically self-tunes to the most frequency that is present in the input. Of course, there are some parameters like the damping and a gaining factor over that we can play in order to be able to make the convergence faster, slower, or slower. So, of course, we also apply some tricks like handing windows in between different chips to make the signal more continuous. And what you see that if this is the frequency and this is the time of the chirps, you see that the neurons is initialized at 50 hertz, for example, internal omega starting. You have a target at 200 kilohertz, and the neurons slowly converge after only 16 chirps to the right frequency. So a single neuron now is performing the spectrum and is telling us what is the range of the target. Of course, typically you have multiple targets, and when you have multiple targets, you would like multiple neurons to converge to all of the different peaks, like in the first image that we saw. So for that, we introduced a feedback mechanism in which you have several neurons in parallel, all adaptive, resonate, and fire. But then whenever you send the input frequency, which is the full chirp, after one neuron converges, let's say, or whenever one neuron converges to a certain frequency, you would sum this up and then subtract the frequency of the neuron that converge, so that then the other would converge to a different frequency. So if you have two neurons, what you do, you basically subtract the frequency component of the first neuron to the incoming signal, and then the second neuron would not see the previous one. So it would naturally converge to the next most prominent frequency. So here you see a simulations of what I'm telling you. Those are two resonate and fire neurons. Those are two fixed target at fixed distance. And what you see the evolution of the frequency of the neuron to converge to the two target. Of course, this works well also with 6 targets or with multiple targets. But now this is fully streaming. We don't have to do buffering, and the neurons naturally converge to the target frequencies. So now we have one single adaptive resonate and fire neurons for a single target. You can have the number of adaptive resonate and fire, as many targets as you are interested in the scene. It is online, low memory. We don't need to buffer anything. Everything is streaming. And it is also low latency because you can do this in real time. You don't have to wait to process the full frame and do the double FFT before you update the state of the neurons. Of course, you can also do a first FFT only for the range, and that's what we saw. You can couple a second bank of resonate and fire neurons that would work on the output of the first one in order to do the velocity estimation, because it's a double FFT, right? As soon as you do a spectrum in one dimension, you can also apply that in the second dimension. So you basically measure the phase change in this case, and you have 1 neuron per target velocity. So if you have one target, you would also add a neuron that measures the velocity of the specific target. Velocity can also be 0, of course, or low. And receives only 1 sample per chip. So everything is streaming now. You don't have buffering, and you don't have anything like that. So here you see actually an example with an automotive data set in which we had 1, 2, 3, 4, 5 adaptive resonate and fire neurons and 4 very prominent targets. So those are actually targets. So this is range. So this is the distance from the radar. And this is the speed. So what is the speed of the target in the environment? So is it positive or negative? Of course, the speed can be, because you can move close or further. And what you see that the neurons immediately converge to the right range after few iterations, as well as the speed. The neuron converges quickly to the correct speed of the target. Of course, we had more neurons than target in this case, and the neurons that, let's say, don't represent that are not converging to a point are the ones that cannot follow the signal because there is no target there, right? So you can see that they stay. It's easy to track them to know which one they are because they're not converging to a target. Of course, in order to also reduce even further the data rate, what we can even do, we can even have a threshold crossing operations on the membrane potential or on the complex value of the oscillator and make them spike. And what you would see then, you will see that neurons that converge to the right frequency, so they don't need to change their frequency, their let's say internal oscillation frequency, they immediately go silent, meaning that they reached the target measurement and they don't need to send an update. The one that don't converge instead, they still have sparse spikes. So this can also be used later on to perform, let's say, more than just range and velocity estimation. Of course, all of this system with just, let's say, 5 neurons, you are basically doing target distance and velocity estimations, but also you're doing associations with so it's like a CFAR plus FFT, if you are familiar with the radar terms. So in the end, how does it perform in terms of computational complexity and memory footprint? If we compare this to FFT, N is the number of target, and L is the number of samples that you have in a chirp. Regarding the memory footprint, our algorithms only scales with the number of adaptive resonating fire neurons that you have, instead than the number of time point that you have. Also, computational complexity, it can have an advantage depending on how many targets you have in the scene. But typically, you don't have more than a few targets. So the outlook, of course, is that this is sample by sample processing. You can scale with the number of targets. It's a very simple signal processing algorithm that is a dynamical system. It has low memory and online computation. It's targeted for neuromorphic systems, like, for example, the Intel OIHI2 or Spinnaker board. You can implement, and they have already implemented, this type of neuron model, and you can have them implemented efficiently with those platforms. We're also working on FPGA implementations, and now we are also looking at, whenever you have multiple antennas, how you can do beamforming. Of course, this work was mainly done by the PhD student Stefano Chiavazza. This is the team. We have a couple of vacancies, so if you are interested also in edge, neuromorphic, or please contact us. And we have done this work in collaborations with TU Delft and Intel now, because we are mapping it into the Loihi chip for a national project. Before concluding, if I still have a bit of time, I'd like to... You still have actually 5 minutes. Perfect. So I can also show you a demo, which is also nice to see, hopefully. If the... more time, I just checked the schedule. Okay, good. Just while presenting, perfect. So here you see a small, this is a software demo. I will show you then a real radar that I have with me, but software demo also is first to understand. So what you see here, you see the chirp, simulated chirp coming back from the environment. And here you see 4 adaptive resonate and fire neurons. And this is just the velocity and the range. So this is the internal ZDT, this complex value, over time. Here I have several parameters. I can perform Henning window on the signal in order to smooth it out at the edges so that the continuous update is smoother. And then I have 2 targets. The first target is at 7.2 meter at a speed of 6.31 meter per second, minus. It's moving in the minus away. The target 2 has a speed of 5.82 meter per second and a range of 3 meters. So the target in a traditional signal processing double FFT would appear like the color image here. This is one of the targets, and this is the second target, because this is Doppler velocity, and this is range in meters. The 2 white circles here are the state of the neurons combined, range and velocity, x and y. That's it. So there is no more to this network than just these 4 neurons. So if we now start changing, let's say, the positions of the second target, you see that they start to move, right? And they also interact in nonlinear ways, the two neurons. So you see that they kind of track the velocity. We can update the parameters, for example, in this case, the speed at which the neurons move or converges, right? You see kind of they follow the target. And this is done only through these dynamical systems with 4 neurons. Of course, we are happy to do software simulations, but real life is more exciting. So we are trying, okay, good. So we are trying now to run it. So what you see here, you see traditional FFT. So this is just the range. So this is range in meter. And that's what you get when you do the FFT on a frame of radar data. You see a peak over here, 1.3 meters, probably is the ceiling, because it's actually it's looking at this direction, it's over there. And this is the only thing that we do with the state of the neuron, so updating the neuron state. And you see that the state of the neuron state is 1.8 meter. That's probably the ceiling. And this is actually the range over time for this neuron. So if I start moving the board probably closer, then you will see that the range becomes 1.2 meter, 1.3, and then it goes further away. Of course, I only have one oscillator. I can add more oscillators, right? 2, but then I need to have 2 targets, because otherwise they... Yeah, now you see 2 targets, like probably the camera but you can add multiple targets. Of course, as I say, this is only the first FFT, but you can also do the second FFT. Hopefully this shows. Yes, this also works. So this is the Chirp coming back from the radar. This is a 24 gigahertz radar, inexpensive one. We also did the PCB, so probably it's very noisy by our PCB. We're not super expert in doing this. And what you see here, you see the micro Doppler, so the range Doppler, which is the range and velocity. So if I start moving my hand, you should see these oscillations very close, at a very close distance, and this basically means that we are tracking with the, we are tracking the signal. There is no adaptive resonant amplifier neuron in this demo, but I think I have another one, but I can show you later. I have to figure out where that is. Yes. If there are any questions, and if we have time, I'm happy to answer.
One question.
Yes.
So the signal you get is the frame of the chirps, right? So it's not the frequency contents of the chirp; it's of the radar signals.
So what you get at the so what you get also, you can see it here. It's chirp by chirp. So we process every incoming. Basically, the radar emits this increase in frequency.
Time domain data.
It's a time domain data. It's not a. So basically, all the chirp that we get back, we send it in sample by sample in the adaptive resonant amplifier, and then that's resonant amplifier will converge to the signals. So basically, this signal here that you see at the top is what we use, and this is the time domain signal. And we process only, so this is the maximum buffering that we need to do. That's the, plus the state of the neurons, right, of course. Yeah. You have one? Do you want another one?
Yeah, I can ask one.
Yeah.
Like, what's the adaptation? Can you show again the adaptation equation?
Yes, of course. You're very technical, Manolis, huh?
I can ask it offline.
No, it's fine.
I think it's intriguing.
Yeah.
And then the second question is like, how would that work with gestures, actually? Because there, the second layer has to adapt, as you said, to the face.
So typically, okay, two questions. So this is the equation. You wanted to say it?
Okay,
There are many parameters
just
here.
give
Yeah. So this is basically the input signal. It's a complex I and Q value from the antenna. That's what you get here, the imaginary and the real part. We scale it, we normalize. We see that we can also live without normalizations, actually. Then we have 2 parameters, right? And they serve to update the omega of the neurons, which is then used to calculate the neuron update. It's just, yeah. This is not a new system in per se. It's adapted from a continuous versions of, it was published in 2006. And it was also used for audio signal, I believe. This can also be applied to audio signal, by the way. Whenever you have to do frequency spectrum analysis, you can use such a system.
Is it not slower in settling?
Of course, there are some parameters that you need to tune. The lambda here, the decay, will tell you how fast or how slow it is. And also, if you have 0 input, right, how does the system behave? It's a question. But in real life, as you see from the radar, there is always some noise. There is always something. And actually, noise helps in our case to push the neurons to different peaks.
It's like an annealing process, the way I see it.
Yeah, it's basically a dynamical system that goes to the minimum of the.
Correct, you could take a trade-off between a couple of original neurons. With this system, so reduce the the frequency range they can settle, and and just use still several neurons with different ranges. For
Yes, you can also
to have a trade-off
yeah, you can.
settling time.
Okay, indeed, a very good choice. Instead of just going with one, there is always an intermediate, right? And Hank knows where are the trade-offs. So you could, let's say, let this neuron only adapt to a certain frequency range and have multiple bands for them. That you could do. Yeah, we're interested in the extreme. We want to go to extremely minimal.
Yeah, but you did not mention what is the price you pay in settling time.
Yeah, that's something that it's also difficult to estimate. It's also difficult to estimate because there is a trade-off there. If you look at this one,
You could just compare it with two.
yeah, no. But if you do a fast Fourier transform with 16 chirps, right, you would get probably a certain level of noise here, right? And if you do it, this one, you basically have an answer at each chirp. So something that you cannot do if you have like a memory buffer, right? Because you always have to process the full frame. In this case, you have this trade-off between latency and the precision as well.
Yeah, you need 16 for the velocity.
No, 16 chirps in order to converge to the exact frequency. But if you look at it after a few chirps, you are close. So there is also a trade-off there, right? That's the speed that you were looking for.
We are out of time.
Okay, out of time, but we can discuss later.
Okay,